Welcome to the Deep Dive. We're to get our hands dirty with a new topic today.
Yeah.
We're diving into the world of cause and effect, but not the kind of cause and effect we see every day,
Right, yeah.
Like if I knock this glass of water over, it's going to fall on the floor.
Yeah.
We all get that.
We're talking about something a little bit more in depth.
Yeah,
A
exactly.
little more sleek.
More complex systems, like
Yeah.
the kind that make your brain go, oof.
Yeah,
Oh, wait,
yeah.
just trying to wrap your head around it.
Exactly.
So we're talking about uncovering those hidden causal relationships in complex systems.
Right.
And you've got a fat stack of research here about something called causal inference in time series data.
Okay.
And
Sounds like a mouthful, huh?
to be honest, it's a little intimidating at first glance.
Yeah.
So where do we even begin? Like when you brought this to me, I was like, all right, how are we going to tackle this one?
It can seem a little dense when you come to it at first.
Yeah.
It's like, imagine trying to figure out if rising sea levels are directly caused by increased carbon emissions.
Okay.
Or if there are other factors at play.
Okay.
That's the kind of question that we're tackling.
Okay.
We've got these data sets that unfold over time. That's
Right.
why we say time series, and
Yeah.
we're trying to really decipher what's truly causing what.
Okay, so we're playing detective,
Yeah,
but with data.
with data.
And we can't just look at, event A happened, then event B happened and be like, well, clearly A caused B.
Right. We can't just jump to those conclusions.
Right.
That's the classic trap of correlation does not equal causation. Just because ice cream sales go up in the summer and so do heat strokes doesn't mean that one is causing the other.
Right.
There's a hidden factor there,
Right.
which is that the
Yeah.
rising temperatures.
Right. It's hot. People want ice cream.
Oh.
People are out in the sun having heat stroke.
Yeah.
Okay, so how do scientists try to determine true cause and effect when they're dealing with these more tricky situations?
Well, one way is through controlled experiments.
Okay.
So think about testing a new drug.
Right.
You have a group that receives a drug and a control group that gets a placebo.
Right.
And by comparing the outcomes, you can isolate the effects of the drug itself.
Okay.
But what about scenarios where controlled experiments are impossible, like
Right.
trying to study the impact of deforestation on global climate patterns? We can't exactly plant a whole new Amazon rainforest just to see what happens, or go back in time and stop it from happening,
Yeah.
right?
One
So
thing-
that's where this causal inference comes in.
Right.
We're dealing with what we call observational data. It's
Yeah.
data we gather just by observing the system
Okay.
without directly manipulating it.
Got it.
Now, there are established methods like Granger causality,
Okay.
where you're essentially checking if knowing the past of one variable helps you predict the future of another.
Okay.
But these traditional methods really struggle with nonlinear systems.
Okay.
So those are systems where the relationship between cause and effect isn't just a straight line.
Okay.
And let's face it, most real-world systems are anything but linear.
Right.
They're complex. There's feedback loops.
Right. It's all tangled up.
Yeah.
So how do we even begin to untangle these intricate relationships?
Right.
What are some of the, you've got a stack of research here.
Yeah.
What are some of the new tools and techniques that researchers are developing to try to crack this code?
Yeah.
Well, we wouldn't be diving deep if we didn't explore those techniques.
That's right. That's right.
What are some of the tools in the causal inference toolkit?
So one really fascinating concept is this idea of using what we call shadow manifolds.
Yeah, manifolds. Okay.
Yeah, and it's kind of based on this idea that
It already sounds cool.
it does, right?
Yeah.
It's very evocative.
Yeah.
But the idea is that we can observe a complex system.
Okay.
Like let's say a school of fish darting and weaving through a coral reef.
Okay. I'm picturing it.
Yeah.
Beautiful underwater ballet.
Exactly.
Yeah.
But let's say we can only track the position of each fish.
Okay.
We can't see the currents, the water temperature, or any potential predators that might be influencing their movements.
Right. We don't have all the variables.
We just have this limited kind of porthole
Right.
into what's going on.
Okay.
So how do we account for those hidden variables if we can't directly observe them?
Right.
That's where the shadow manifolds come in.
Okay.
They're based on this idea that even if we can't see all the variables at play, we can still get a sense of the system's underlying dynamics by just analyzing how the variables we can observe, like the fish's positions, how they interact with each other over time.
So it's like deducing the choreography of the ballet just by watching the dancer.
Yes, exactly.
Okay.
And that's what this convergent cross-mapping, or CCM, tries to do.
GCM got it.
So by analyzing those time-delayed relationships
Okay.
between the fish positions, how the movement of one fish influences the others, a few moments later, CCM can essentially reconstruct what we call a shadow of the system's true underlying dynamics.
Okay.
This shadow manifold, as it's called, can actually hold information about those hidden variables,
Wow.
like the currents or the predators that are influencing the fish's movement.
So it's almost like we're using math to reveal a hidden dimension of the system.
Yeah,
Like we can start to see the invisible strings that are pulling the puppet strings, so to
I
speak.
love that analogy. Yeah.
Yeah,
It's
yeah.
like we're peering behind the curtain to see
Yeah.
the wizard.
Okay, but how do we go from this shadow play
Right.
to actually determining cause and effect?
So CCM looks at how well the shadow manifold of one variable can be used to predict the behavior of another.
Okay.
Let's say we're looking at two variables, A and B.
Okay.
If we find that we can successfully predict the future of variable B using the past of variable A,
Okay.
it suggests that A might be a causal driver of B.
So we're not just saying that they're correlated.
Right.
We're saying that there's this deeper causal link
Yeah, it suggests this deeper link.
that we've uncovered through this process.
Exactly.
That's really cool.
It's pretty wild, right?
Yeah. Are there any limitations to this approach?
That's a great question, and it leads us to a really interesting point about causality itself.
Okay.
You see, the way CCM was traditionally applied, it used both past and future data to make these predictions.
Okay, so we're kind of cheating a little bit.
Well, yeah, it's kind of like looking at the answer key before taking the test. It's like saying you knew it was going to rain because you got wet.
Right.
And that created a bit of a philosophical conundrum because the traditional view of causality says that the future can't influence the past.
Right. If we're looking at, A causing B,
Mm-hmm.
we can't be like, well, B happened, so that means A. It's like, what came first, the chicken or the egg?
Right, exactly. And so researchers realized that this reliance on future data was a real sticking point.
Okay.
So they developed a modified approach called causalized convergent cross-mapping.
So we're going to add a C in there.
Add a C in there.
CCCM.
CCCM, exactly.
Okay.
So CCCM only uses past values for prediction,
Okay.
which aligns much more closely with our intuitive understanding of cause and effect.
So it's like we're not allowed to look at the answer key anymore.
Exactly.
Okay.
We have to figure it out based on what we know up to this point.
Okay. So CCCM sounds like a pretty powerful tool
Yeah.
for unraveling these causal relationships, especially in these complex nonlinear systems.
Yeah, it's a good tool for the toolkit,
Right.
but it's not the only one.
Right, because every good detective needs a toolkit.
Exactly.
You can't just rely on one piece of equipment.
That's right. We've got a lot of other techniques to explore.
Okay, so tell me more about these other tools. What else are researchers using to crack the code of causality?
All right, let's dive in.
So we've got CCCM for those tricky situations where traditional methods fall short. What other tools are in this causal inference toolkit?
Well, imagine you're dealing with a data set so large and complex that it would make your laptop overheat just trying to load it.
Yeah.
That's the kind of challenge researchers face in fields like neuroscience or climate science.
It's like trying to find a single grain of rice in a silo.
Right.
Just massive amounts of data, but you're looking for those subtle causal links buried within it.
Exactly. And for those kinds of scenarios, there's an algorithm called CUTS.
CUTS.
Yeah. It's specifically designed to handle those massive high-dimensional data sets.
Okay.
And it does so with a really clever two-step approach.
Two-step.
Yeah.
Okay, tell me more. How does it break it down?
So it's a coarse-to-fine approach.
Okay.
Think of it like trying to understand a complex painting.
Okay.
First, you might step back to take in the overall composition, the broad strokes of color and form.
Okay.
That's the coarse step. CUTS simplifies the problem by breaking it down into smaller, more manageable chunks.
Okay, so it kind of zooms in on smaller sections of the
Yeah,
data.
you got it.
Okay, then what?
That's where the fine step comes in.
Okay.
CUTS uses something called a message passing-based graph neural network.
Okay.
It's a mouthful, I know.
Yeah, what is that?
Essentially, they're looking for patterns and relationships between the variables in each of those smaller chunks.
Okay.
It's like examining the brushstrokes up close, seeing how they connect and interact to create the overall image.
Okay.
And because CUTS has already done the heavy lifting of simplifying the problem, these neural networks can work much more efficiently.
Right, so it's like we're giving it these smaller, more manageable tasks
Exactly.
so it can do its thing.
Yeah.
Okay, that's really cool.
Yeah, it's a really fascinating technique.
What other techniques are out there that researchers are using?
So another one is called partial cross-mapping, or PCM.
PCM.
Okay, and this is really good at untangling direct and indirect causation.
Okay.
So imagine you're studying the relationship between air pollution levels, respiratory illnesses, and socioeconomic factors.
Okay, so there's a lot of layers there.
Yeah, there's a lot going on.
Right.
PCM helps us to kind of differentiate between those layers.
Okay.
We might find that air pollution directly causes an increase in respiratory illnesses,
Right.
but there's also an indirect causal pathway through those socioeconomic factors.
Right, because if you're living in a certain area, you might be exposed to more of that pollution.
You got it.
Okay.
So PCM allows us to kind of tease apart those direct and indirect pathways.
Very cool.
Yeah, it's a really valuable tool.
So what else is there?
Another exciting development is something called EcoNet.
EcoNet. Okay.
And this is a framework that actually uses multiple neural networks working together in concert.
Multiple. I thought one was enough.
Right. Usually we think about one at a time, but in this case we're using an ensemble of neural networks
Right.
to identify those dominant causal drivers in ecosystems.
Okay, so this would be like in a forest.
Yeah, exactly like a forest.
You've got all these different variables.
Rainfall patterns,
Mhm.
insect populations, types of trees.
It's a lot.
Yeah, and that's where EcoNet really shines.
Okay.
Each neural network learns different aspects of the system's dynamics.
Okay.
And then we combine the insights of all of those different networks to get a more robust picture of what's driving the system's behavior.
So it's like a team of experts
Exactly.
all coming together
Each with their own little specialty.
to try to solve this problem.
Yeah, it's really cool.
That's really cool. And it seems like, after we use these techniques, these tools, we can start to see these causal relationships not just as like a list of numbers on a page,
Right.
but as this like dynamic interconnected web.
Yeah,
We're not just like analyzing data. We're starting to uncover the story that data is telling.
I love that. Yeah, that's a great way to put it.
This has been an amazing journey into this world of causal inference.
It's a really fascinating field.
But I have to ask, what's the so what here? Why should we as listeners care about all of this?
Well, these techniques have the potential to revolutionize a wide range of fields.
Okay.
So in neuroscience, researchers are using these tools to analyze brain activity, to map out the causal relationships between different regions of the brain, to better understand how our brains work.
So it's like instead of just saying, oh, this part of the brain lights up when you think about this,
Right.
we can actually see the pathways.
Yeah, we're going beyond just those simple correlations.
Wow.
Starting to understand those causal mechanisms.
That's incredible.
Yeah, it's really exciting.
What about other fields?
In ecology, these techniques are being used to identify the key drivers of environmental change.
Okay.
Imagine being able to pinpoint the specific factors that are contributing to the decline of a particular species or the collapse of an ecosystem.
Wow. That would be...
That kind of insight could be crucial in guiding conservation efforts.
Yeah, because then we'd know what levers to pull
Exactly.
to try to fix it.
Yeah, we're moving beyond just observation and moving into a place where we can actually start to make more informed decisions.
It sounds like we're entering a new era of scientific inquiry,
I think so.
where we're not just observing these phenomena, but we're actually untangling this web of cause and effect that underlies it.
Yeah, that's a great way to put it.
And it's not just limited to science.
Right, this has applications in economics and social sciences, even in understanding the spread of misinformation online.
Oh, wow.
Yeah, the possibilities really are vast.
So it's like this entirely new way of looking at the world around us.
Yeah, we're asking new kinds of questions and coming up with new ways of answering them.
It's really incredible to think that these techniques that, might seem very abstract at first glance
Yeah.
have the potential to impact so many different aspects of our lives.
Yeah, it's really exciting to see where this research goes next.
A huge thank you to our expert for guiding us through this fascinating topic.
It's been my pleasure.
And to you, our listener, keep exploring those intriguing questions. Keep seeking out those aha moments, and we'll see you on our next deep dive.